Hi again everyone. Welcome to the second lesson for machine learning. Today we are going to dive deep into supervised learning and understand some of the algorithms behind some of the supervised learning tasks. So this is what we want to learn from today's lesson. We want to understand by observing many examples of data, what we call the instances in machine learning of features in the data, paired with the desired output, the targets, the machine can learn the relationship between data and outputs. So using feature target pairs is an important part of supervised learning. We call it supervised because the targets, the answers are also provided to the machine, and so the machine can do some auto marking and see whether they have gotten the correct answer, and if not, they need to adjust their methods in order to achieve the correct answer most of the time, if not all the time. You can think of this as something similar to when you do your math homework or your physics homework, and then your teacher provides you feedback, the answers through some feedback of your homework, and then from there you learn how to the relationship between the questions as well as the answers. So you understand that certain questions need to be solved using certain methods, certain formulas, in order to get the correct output, the answer that you want, or the answer that the teacher wants. So some of the essential questions that you should be thinking about as we go through this lesson is about understanding what are some of the machine learning algorithms for supervised learning, and also more importantly, how do I pick the right one for my problem. The third question we want to answer today is, how do I tune my model to fit the data while being able to generalize to new data. So I'll pick this one apart a little bit more. So what this one is trying to say is that when you have a set of feature and targets, a so-called model answer, right? Sometimes your computer gets so good at predicting the answers for this set of questions that it cannot generalize to new questions. It's as though the machine has memorized the 10-year series, and so if you give it a new question, it gets lost because it's a new question. It doesn't know how to deal with it. So that's not going to be useful in the real world, because you're always going to have new unseen data out there. So this question is here what we want to do is we want our models to be able to fit the data, do reasonably well on the TYS, and yet be able to generalize to new questions to get the answer for those questions as well. So once again, this is the three types of machine learning, the machine learning paradigms: supervised learning, unsupervised, and reinforcement learning. Supervised learning is the one we are going to focus on in this syllabus. So today we are talking about classification, regression. So as I mentioned before, supervised learning is about having the answers with the questions, and then the computer learning how to get from the questions to the answers, right? So a classification problem is when you have discrete answers. So is it spam or is it not spam? Is it a face or not a face, for example? So you see that most of classification questions is either yes no questions, right? But you also have other kinds of classification, like if we are predicting the weather, maybe is it going to be a rainy day, a cloudy day, or a sunny day? 3 answers. Okay? Or a very famous problem is to recognize handwritten digits. So there you have 10 answers from digit 0 to digit 9, right? So that's also a classification question, because you can group, or you have different categories for different answers. Regression, on the other hand, is where we try to predict continuous answers. So instead of neat categories of answers, the answer is a continuous number, possibly a decimal place number or a integer. So examples of that is when we want to predict the height of a plant given the past data, for example. Or if, let's say, I want to predict the price of a house depending on how many rooms are in the house, what area, whether it's a good neighborhood or not, kind of thing. So that is what regression is about, predicting continuous data, maybe usually a number, a decimal number. Unsupervised learning, if you remember, is when I do not have any answers. We just want the machine, the computer, to analyze the data and pick up certain patterns, or if there are any patterns at all in the data. So unsupervised learning is used a lot for clustering. Clustering means you're giving the computer this much data, you're telling, okay, group the data. Okay, if I want the computer to put it into two separate groups, how would the computer do it? So from there, clustering is done for different reasons. Sometimes you want to see whether there are any patterns in the data or not. Sometimes the patterns are not even obvious to us as humans, but the computer can see, because there's a lot of, maybe there's too many features, too many variables, and you can't really analyze it by hand or by eyeball. So sometimes you need a computer to take a look at the data and see, okay, what is similar, what is not similar. And then maybe they'll be able to find patterns that humans may have missed because there's just too much data for humans to handle. Okay. The third kind of machine learning is reinforcement learning, and reinforcement learning is about learning from your past mistakes. So here you don't really have a lot of data being fed to the machine. You just have a reward system that rewards the machine if they get the correct answer and punishes it if it doesn't get the correct answer. So this is in a way also similar to how humans learn, right? Sometimes when you do something that is good, your parents will reward you, or you're rewarded by the law, okay, for not doing something, or it's not punished by the law if you do not break the law, right? So you are in a sense rewarded for good behavior and punished for doing something wrong, right? So likewise in reinforcement learning, if you think that the computer is acting or producing a result that is desirable, you give it a reward. If it's not desirable, then you don't give a reward. Example is, if you want the computer to learn how to play a scissors paper stone game, the reward could be given for winning the game, and so-called punishment will be given for losing the game. So from there, the computer will start to ideally learn certain traits or certain tricks that can help it win more often than not to win. So as mentioned, we are focusing on supervised learning for this lesson as well as for this syllabus, because supervised learning is the foundation of machine learning. However, many modern techniques, the trendy topics now are all in supervised learning, and especially reinforcement learning nowadays. So if you are interested, I do encourage you to read up a bit more about these two. So this is an infographic about what supervised learning is about. You give the machine labeled data, okay, those labeled with the targets, right? So from the labeled data, the computer will then be able to learn to distinguish between cats and dogs, even if you give it new data that it has not seen within the training phase, right? And classification is when I sort the items into categories. Regression is when I identify a real value, like how much money or the weight, the height. Okay, so as we have talked about for however long, okay, supervised learning requires you to have features and targets, okay, paired together. Okay, there's no point having a set of targets and the computer doesn't know which answer goes to which question. Okay, so the computer will learn how to figure out the relationship, how to get from the given a certain set of features, what target is should be output or predicted. Okay, and then so when you test the machine with certain values of features, okay, even for unseen instance, it will be able to predict the targets for each instance. So what this means is, if I give it a new question, okay, previously unseen question, it will be able to predict a reliably accurate answer. So once again, the difference between classification and regression, where classification is when you have discrete targets, and regression is continuous. Okay, and we have examples there. Classification is predicting whether email is spam or not spam, and regression is maybe predicting dollars, right? So real values. So here are some of the common algorithms used for regression. This part of the lecture will talk about some of the popular algorithms, okay, for regression and classification. So we'll start with regression, and we'll talk about linear regression. Okay, linear regression, although the name sounds so complex, so profound, but actually this is something that you've already been doing in especially your physics practical lab-based sessions, right? You get the data from your experiments, you plot the data, and then you draw the best fit line, right? So that is literally what linear regression is all about. You plot your training data, you draw your best fit line, and then the best fit line tells you what target to predict based on the features. Okay, so this is a very simple, the diagram here shows a very simple example. Let's say I only have one feature, and then the y values are the targets. So I plot them all out, and then I find that best fit line. So if let's say I have a new feature, let's say around here, yeah, I can read off the line to see what y value I want to return, right? And of course, the parameters that the computer has to learn is the m and the c in order to get the best fit line in the right gradient, okay, the right height as well. Yeah, so this is where your learning takes place. It learns the m and the c. Okay. Of course, this is a simple example. Usually you will have more than one feature, many features, sometimes maybe up to 10, 20 features, depending on how complex your data is. So this is a simple example for you to visualize, okay, but the procedure is the same no matter how many features you have, just that you will not have a simple two-dimensional line anymore. Okay, if you are interested, the mathematical term for a 10-dimensional or 20-dimensional line is called a hyperplane. So what happens if you have more than one feature? It's not just y equals to mx plus c anymore. You have to do what we call a linear combination of the features. What that means is every feature x1, x2, x3 will have its own m in front of it, coefficient m. So m1, m2, m3. And the task of the computer is to learn, to find m1, m2, m3 as well as c through training with the data. That's the only regression algorithm we're going to talk about, because regression algorithms do tend to be a bit more complicated and difficult to visualize. We'll move on to classification. Likewise, the idea here is to be able to show you some of the math behind the algorithms. The reason why we want to do this is because we want you to have a better understanding how machines can learn, instead of just okay, the algorithm is unknown and then you just feed it data, out comes a prediction. Okay, we want you to have a deeper understanding as computing students. Right, so classification, the ones that we want, the algorithms we want to focus on, the four ones with bigger font on this page. Okay, we'll start with decision trees. Decision trees tries to model a human's thought process, okay, in a flowchart-like manner. So for example, if let's say I want to do a simple decision of what do I want to eat in the canteen today for recess. So my decision process could be something as simple as, okay, I'll go downstairs and I'll take a look at the noodle store. Okay, if the noodles auntie is selling my favorite spicy noodle, whatever, okay, some spicy noodles, okay, I will go and eat the spicy noodles. Okay. Else, if she's not selling the spicy noodles today, then I will go and look at the Malay store. Okay, if the Malay rice store is selling roti prata, I will eat roti prata. Else, I will do something else. Okay, so it's like a bunch of if-else statements, right? And that is sometimes how we make decisions. Okay, based on the information we have. Okay, if this is available, I will do this. If not, I will do something else. Okay, sometimes other things that influence your decision could be: am I eating with my best friend today. Okay, if I'm eating with my best friend, then my best friend always eats roti prata, so I will be eating roti prata with her. Okay, otherwise, if I'm not eating with her, then I will eat. Maybe I'll go to see the Chinese rice store and see if they have chicken cutlet. Okay, so things like this, or maybe another something else that can influence the decision is how much money you have in your wallet today. Right, so that is how a decision tree works. This diagram here shows a decision tree with some of the terminologies there. So sometimes when we talk about the depth of the tree, that means how long your tree is. Okay, how many decision nodes you have. Okay, the root is the very first node. Okay, I know it's a bit weird, but in computer science, we always draw our trees upside down. Okay, so the roots are up right on top and the leaves are at the bottom. Okay, so yeah, get used to it. Okay, the bio students are going to kill us, but it's fine. Okay, we'll survive. Okay, so you can see here that this is a decision to do something. Okay, the actual problem was to see whether I want to go and play tennis. Yeah, so here I have. So here I take a look first. Is the weather sunny or rainy or overcast? If it's sunny, then I check whether it's humid. If it's humid, then I will. If it's not humid, I'll play tennis. If it's too humid, then likely I won't. If it's overcast, I always go and play tennis, no matter what, whether it's humid or rainy or windy. Okay, and if it's rainy, I'll go check the wind as well. Okay, so the features are the ones in the blue circles or ovals. Okay, whether the outlook, whether sunny, rainy, overcast, humidity, the wind as well. Okay, and your targets are yes or no, whether I want to play tennis or not. Okay, so the decisions may look deterministic. What that means is whenever it's sunny and it's very humid, I definitely won't play tennis. Okay, that is the decision that I'll always make based on this tree. Okay, however, if you look at the data, right, okay, you can take a look at the node in the red circle. Okay, you can see that there are 2 no's and 1 yes. Okay, so based on the training data, right, there was twice that I did not go and play tennis when it was sunny and it was humidity more than 75, and there was one time that I did go and play tennis. Okay, under these conditions. So if you look at the data, it's derived from probabilistic ratios. What this means is I didn't do the same thing whenever the conditions were like that, right? I didn't do the same thing all the time. Okay, twice I didn't play tennis, one time I played tennis. Okay, however, to in a sense simplify the whole system and in order to make a prediction all the time, I will just go with the highest probability. So 2 times out of 3, I won't play tennis under these conditions. So if I were to encounter a new scenario where it is sunny and it is humid, my machine, who has learned from this data, would also inform me that no, I will not play tennis today. I should not play tennis today. Yeah. Okay. So sometimes it is a bit I mean, sometimes when you work with data, you will have outliers. Okay, so sometimes the data that you receive does not fall neatly into categories, and that's natural because in life there's always a bit of chaos. There's always a bit of unexpected things. Okay, even when you do your science experiments, no matter how much you try to control your environment, sometimes the data fluctuates a little. So that is normal. Okay, and that's also why when we do machine learning, it is almost impossible to get 100% outcome. Yeah. Okay. So yeah, what this slide is trying to tell us is that even though there is some kind of chaos, some kind of unexpected data, the machine should be able to do reliably well. Okay, and that's of course if we have enough data. Okay, imagine if we only had so little data cases where I only have 1 no and 1 yes in this node, then I cannot make a proper decision, or the computer cannot make a proper decision. So how do decision trees, how are they formed? Okay, number one, of course, I need to decide on the feature to split my data. So once I've decided on that feature, I'll split the data to subsets, and then at each node, I'll continue to split it further, okay, until each subset is pure. Okay, pure meaning all the instances are one target, okay, or until you run out of features to separate on. Okay, if you run out of features, then you just have to make a decision there and then already. Okay, so there is decision trees, which is deterministic in nature, meaning that the outcome when you are doing predictions, no matter if the input is the same, the features that you give it is the same, sunny and high humidity, the outcome will always be the same. Okay, no, I won't play tennis. Okay, that is what it means by having a deterministic deterministic classifier. Okay, we look at another classifier called the k-nearest neighbors. So k-nearest neighbors requires you again to plot all your data, okay, similar to what you do for linear regression. The difference here is that your x and y axis are both features. Okay, so the targets are not plotted in this way. Okay, but the targets are inherent in the plots, because you do know which ones are belong to class A and which ones belong to class B. Okay, so when you plot them, ideally you will see that the class A groups up together and class B also group up together, right? Because they are technically distinct, right? Otherwise, why do we have two different classes, right? If you do not have that strong distinction, that means that your features are not good enough. Okay, you need to have better features that can reliably differentiate from the two classes. Yeah. So once you plotted all your points, okay, with all the features, okay, then we will also need to plot the unknown example. Okay. So the unknown example shown by the question mark here is plotted on your graph as well, and then you want to find the distance between this unknown and the nearest points around it. Okay, so that's what it means by nearest neighbors. Okay, neighbors here means the points that are closest to that point that you want to find out about. So you find all the distances, okay, and then you calculate based on a certain value of k. So let's say I settle on the number 3, k is 3. Okay, so k is a predetermined number, right? So let's say I decide that k should be 3. So I look at the 3 points that are closest to my question mark. So it happens to be these 3 in the circle, in the dotted circle. I have 1 class A and 2 class B. So 2 is 1 versus 2. Class B will win. So I will label my question mark with class B, because it is closer to 2 of my class B's compared to 1 of the class A. Okay. So when you do the k nearest neighbors, you may also notice something about k. Does this work very well with even numbers? I think you can imagine what was going to happen. Yeah. So this k, as I mentioned here, is a predetermined number. What does that mean? It's a number you decide. Okay, the user, the person who is doing the machine learning, the person who codes the machine learning program has to decide what I want to use for k. So if I were to change k into the number 5, for example, okay, the class of this question mark may change. Okay, or if I want to change it to 1, for example, even I can also use 1, and then the class may change. So what k you choose also makes a difference of how reliable your classifier is going to be. Okay, so those are the 3 steps. Number 1, I plot all the training data based on the value of the features. Okay, then of course I may want to do a different coloring for the class A and class B. This one also is able to scale up to to more than 2 classes as well. You just have to label them differently or color them differently. Okay, then I plot that new unseen data, okay, the question mark, and then I calculate the distance, okay, between the points, the known points and the unknown point, and then I pick the tree or the k number of points that are closest to the unknown, and then I label it with the majority of those among those k. Yeah, okay. So how do I calculate the distance between 2 points? Okay, if you have forgotten, please go back and revise your coordinate geometry. Okay. All right. So k nearest neighbors is just like that. Okay. It is also deterministic because the program will always give me the same answer for the same value of k lah. Okay, it will always give me the same answer if, let's say, I have another unknown with the same coordinates as my question mark here. Okay, as long as I give this question mark's coordinates, it will always give me the same answer. Okay, that's why it is deterministic. Okay, now we can see an example of a probabilistic algorithm. So logistic regression, okay, don't be fooled by the word regression in the name. Okay, logistic regression is actually a classification algorithm, not a regression algorithm. Okay, the reason why regression is in its name, regression, if you understand the math of it, regression just means trying to fit a line, okay, doing a best fit line. Okay, so here we're not doing a linear best fit line, we're doing a logistical best fit line, okay, a S-shaped curve. Okay, so how do we do this? Okay, first you need to have binary classes, okay, either 1 or 0, okay, where passing the test is a 1 and then failing the test is a 0. Okay, so once you have this 1 and 0 already, this also represents so once you have this 1 and 0, okay, the features are on the x-axis here. The x-axis here in this example is the number of hours you studied. So depending on the target feature pairs that you have, okay, you will plot on this. It's a very strange graph, I understand. Okay, so you plot on this graph either on this line here or on this line here. Okay, depending on how many hours studied. So this person represents someone who studied 0 hours and then he failed. Okay, this person probably studied maybe 1 hour and then he also failed. Okay, this person studied for 5.5 hours and he also failed. Okay, on the other hand, these dots represent those who pass because the target is test pass is 1, the value is 1. This person, he studied for maybe 1 hour and he passed. This one studied 2 hours and he passed. This one studied 6 hours and he passed. Okay, so that's how I plot on this graph. Okay, it's a very strange graph, I understand. They don't line up into a straight line or even a curve. Okay, it's either 0 or 1. It's like a all or nothing kind of thing. Yeah. So based on all these points, how do we actually fit a graph? Okay, you notice the graph, the S shape here, does not really pass through all the points. Yeah. So how do we actually get this done? We use a formula like this. Okay, so we computed a linear function. Okay, put this z into the sigmoid. Okay, and then the computer will just do the automatically training of the values b and c. The b and c is learned by the computer. Okay, you don't have to actually put find the values yourself. So the computer will find the values b and c that create the best fit of this sigmoid curve. Okay, and then the reason why we use the sigmoid, okay, the reason why it's like that, right? Why we use a sigmoid is because a sigmoid, the smallest value is 0, the biggest value is 1. Okay, and that is very nice to model for us the probability of passing. So on the lower end here, the probability of passing is very low, close to 0, and on the higher end, the probability of passing is closer to 1. So you can see roughly the more you study, the more likely you are to pass. Okay, of course, the data is not so neat, right? There are some people who studied very little and still fail. There are some people who studied a lot. Some people studied very little and passed, but there are also some people who studied a lot and still fail, right? But generally, you do see the trend. There are more people studying and passing than those who studied and failed. And likewise, there are also more who didn't study that much and failed compared to those who studied and didn't study and passed. Yeah. Okay. So that's why we use the sigmoid, the minimum is 0, maximum is 1, as opposed to a linear regression where you have values exceeding 0 and exceeding 1. That's kind of stupid because we are talking about probability or the proportion of the students passed. Okay. So again, what if you have more than one feature? Okay, this is similar to what we did for linear regression as well. We take a linear combination of the features, and then your computer will train for the values M1, M2, M3 as well as C. Okay, these values should be learned by the computer automatically, so that when you give it new data, it will use this formula to find the probability of passing. Okay, and therefore you can tell whether this person is likely to pass or not. Okay, so the reason why the logistic regression algorithm is considered a probabilistic algorithm, okay, is because you get what you get back is a probability of passing. Okay, it doesn't tell you straight up whether you're going to pass or fail. It tells you how likely you are to pass. Okay, and so one thing nice about this is that you can adjust how lenient or how strict you want to be. Okay, so if let's say you want to favor being more reliable on passing, then I may want to put the pass mark at maybe higher than 50. So anyone that score anyone has a probability of 75%, passing probability of 75%, I will mark them as I will classify them as having passed. Right. So that is a more strict criteria for passing. Okay, and the reason why we want to do that sometimes is because we want to sometimes we need to be more accurate for a certain class than another class. Okay, so for example, if the COVID test case, if let's say if there are many test cases or many test kits that tell people that, oh, you have COVID, when actually they don't, people are going to lose faith in the test. Right, so sometimes you want to have more strict. You want to be more certain that this person actually has COVID before you tell them you have COVID. Okay, on the flip side, perhaps because you want to be more cautious, you want people you don't want people to have to tell people, oh, you don't have COVID when you have COVID, when they actually do, right? Because there's dire consequences if this person is out there in the community, they are still infectious, right? So you may want to be more strict or more lenient if you're not sure whether this person has COVID. Maybe you just want to say, okay, you have COVID, okay, plus maybe take another test, or please be careful, something like that. Yeah, so that's the nice thing about probabilistic classifiers. You can adjust how strict you want that criteria to be, or how certain you want the test to be, in order to before you make a classification whether this person will pass or won't pass. Yeah. Okay, the last classifier we're going to talk about is the support vector machine. Support vector machine, the name sounds very complicated. Okay, what are vectors? What are support vectors? Right. So for simplicity's sake, we can just say that vectors are straight lines. Okay, or hyperplanes if you have more than two-dimensional. Okay, so the goal when you have when you make support vector machines is to separate your plotted points into two classes. Okay, so it starts with plotting the points, similar to what you do for k nearest neighbors. Okay, but here instead of finding the nearest neighbors, you want to draw a boundary line. Okay, a boundary line to separate the two classes. Okay, and unlike k nearest neighbors, support vector machines only work for two classes. Okay, so here I want to separate my stars and my dots. Okay, the question is, which line best fits the job? Okay. You may have answered B, okay, because all the stars are on the left of B and all the dots are on the right side. Okay, so this is a very good boundary line. Okay, So now I have 3 boundary lines. All of them do the same as what we did, what B did previously, right? Okay, all the stars on the left, all the dots on the right. Okay, so now I ask you another question. Okay, which line best fits the job to separate the stars and the dots? Okay, so all of them fit the description, as I mentioned. Okay, but C does it best. Why? Because there's a wider margin between C and the closest stars and dots. Okay, as opposed to B, which is very, very close to this, that one star, and A, which is also very close to that one dot. Okay, so with that bigger margin, okay, we have less chance of misclassifying, because as I mentioned, there's always chaos in your data. There's always uncertainty, the noise in your data, right? That's what we call it. So sometimes maybe this star was actually a bit of noise, okay, because it's closer to the dots. Maybe it's actually an outlier of sorts. So we want to be as certain. We want to give a wider margin to the closest dots and stars, so that if let's say these stars and dots that are close to the margin, close to that boundary line, are actually misclassified or actually noisy data, we can still the classifier can still work reliably well. Okay, so here I have one star that is very, very far away from the other stars. Okay, and I want to ask you the same question: which line best fits the job? Okay, I'm going to give a bit of wait time again. So remember, the goal is to separate the two classes, the stars and the dots, with a straight line. So the line that does that job is A. Why? Because all the stars are on the left of A, all the dots are on the right of B, right of A, as opposed to B, where you have one star on the right side, mixed up with the dots. Okay, so B might look better because it kind of it seems to have a wide margin and all that, right? Okay, but it does misclassify this point. Okay, so SVM, support vector machines, okay, doesn't really do well with outliers. Okay, so I do agree with some of you who said B. Okay, your B classifier looks better because it has that nice white margin from all the stars and all the dots. Okay, as opposed, and A is kind of slanted. Okay, there's so much space at the top here, right? So however, because of that one outlier, it has skewed the entire boundary line. So there are ways around it. Okay, but then the version 1.0 for support vector machines does very badly with outliers. Okay, having said that, support vector machines is still considered one of the most popular classification algorithms in use, okay, and one of the best out there. Okay, so what is SVM? Okay, SVM is talking about wanting to find that decision boundary, okay, that line that can separate the two classes, and not just separate them, but to get the widest margin between the line itself and the two nearest points. Okay, so the nearest points to that line, that boundary line, are called support vectors. Okay, so that is my description, my quick description of all the algorithms that we have talked about. Okay, here's a quick summary. Okay, regression, we only have linear regression, so that's good for data of linear relationship. Imagine trying to do a best fit line for an x-square graph. Okay, that's not going to work, right? Okay, but if you want to do non-linear relationships, it can still be done, just that you need to modify your algorithm. Okay, decision trees can actually be used for both regression and classification, although it's a bit more popular for classification. Okay, so decision trees is nice because it makes the rules for classifying data explicit. Okay, you can hard code that as a bunch of if-else statements as well. Okay, but decision trees are also very prone to overfitting. Okay, I'll talk about what overfitting is in a short while. Okay, finally, you have the three algorithms for classification. Okay, some of them can actually be also be modified for use for regression. Yeah, k-nearest neighbors being one of them as well. Yeah, okay, so k-nearest neighbors is also very intuitive, like your decision tree, easy to implement, but it's also very sensitive to noise. Okay, so if let's say I have one point that's very close to my unknown, that is a noisy point. Okay, it is an outlier. Okay, then I will not be able to reliably classify my question mark, right? It's also sensitive to unbalanced data sets. So what if I have a lot more class A than class B? Then proportionately, I'm never going to be able to, very hard to get a majority of class B, right? Because there's so many class A's, right? So that is the downside of the k-nearest neighbors. Logistic regression is good for data that's linearly separable. Okay, so data that reliably falls into one category or the other category. Yeah, but because when you have you don't have mixed data like we had in our graph, right, where sometimes you study a bit and you still pass, or you study a lot and you still fail, right? That is not linearly separable. Yeah, so logistic regression works well when it's linearly separable because it can give a very, very good prediction of whether you're going to pass or fail. Okay, support vector machines is also good for linearly separable data, as you see, because you want to have that boundary line. Okay, it's also the least prone to overfitting your data. Okay, again, I'll talk about overfitting in a short while. Okay, yeah. Okay, so before we talk about overfitting, or before we can understand what's overfitting, okay, I want to talk about parameters versus hyperparameters. So parameters are actually things that your computer, your algorithm, your machine will learn automatically through the training. So as I mentioned about the best fit line, trying to find your M and your C, those are parameters that your computer will learn through the data. It would try different values and see which is the best value to output as its linear regression line, or maybe your logistic regression or your support vector machine. Yeah. Okay. So those are parameters that the computer will learn automatically through training. Okay. But hyperparameters, on the other hand, cannot be learned through training. You have to manually tune them, manually change the value, and then observe whether the accuracy increases or decreases to determine what value you want to use. Okay. When I say cannot be learned automatically, that doesn't mean that it cannot be found through a certain automation process of using a for loop. Okay, so sometimes the way that we find hyperparameters is to pick a few values that we want to try, okay, put them in a for loop, ask the computer to try to fit the model for each value, and then we pick the best. Okay, but that is still not automatic because we are forcing the computer to try all of them, and then brute force in a sense, and then we ourselves, we still have to pick which one we want to use. Okay, so examples for hyperparameters is maybe the k in your k nearest neighbors, how many nearest neighbors you want to use to determine your question mark. Okay, and then the depth of the tree as well, the depth of the tree in your decision tree model. Okay, so let's say I don't want a very deep tree, I want a very short one. Okay, then you can also decide that as well. Okay, sometimes you may only want yes/no answers for each node. Okay, so is it windy? Question mark, yes and no. Is it sunny? Question mark, yes or no. Okay, as opposed to what we had, which is the weather outlook. Okay, is it sunny, rainy, or overcast? Okay, so each has its advantages lah. But that is a decision that we as a programmer, the machine learning engineer, we have to decide. Okay, so now we finally come to the point of overfitting. So overfitting happens when we choose parameters and hyperparameters especially, okay, such that they best fit they fits the training data so well that it cannot generalize to new data. Okay, so this is what I mentioned at the start of today's lesson about memorizing your TYS answers, so that when you come across a new question, you don't even know how to deal with it because you only memorize answers, right? Okay, so this is what we call overfitting, and this is not good because your your model is useless for in the real world where you have unseen cases, unseen data. Okay. So this is usually what happens when you have overfitted. Okay, when you train a model, and obviously the training error should drop, because when you're training it, your computer is learning how to get the answers more reliably, right? Then when you test your data, test your model on new data, the test error suddenly rises. Okay, that's unexpected. It should drop. Okay, because you want your model to do better at predicting, right? But if it's doing worse, that means it's just learning the nuances, the quirks, and the outliers in your training data. Okay, so overfitting happens when your model tries to fit all the irregularities, okay, or what we call the noise in our data, our training data, and so that it cannot represent the world around us. Okay, it only memorizes the answers that we give it. Okay, so it's not able to generalize to new questions. Okay, so more formally, this is what it will look like when you have overfitting. Okay, so on the training data, you notice the accuracy is increasing close to 85%. Okay, but on the test data, it is dropping. Okay, test data is where you contains data that the model has never seen before, so it's dropping. So which means that it has overfitted to your training data. Okay, and if you remember the charts earlier, I say that decision trees are very, very prone to overfitting, because it's very easy to make a tree with where each decision leaf only has one training example, right? Okay, so what this means is so if that's the case, right, it fits very well with my it models my training data very well, because it knows that, okay, if I see this, it's definitely this answer. Okay, so like some of you, when you memorize answer, right, oh, you see this, I'm just going to answer A. Yeah, I see this, answer is C. Okay, but then if I give you a new question, maybe I change the numbers, suddenly I don't know how to do already, because I have never seen these conditions before. Okay, so that is the problem. That is the problem of overfitting. And how do we overcome that? Okay, by using a validation set. Okay, we'll be talking about validation set when we do our practicals. Okay, so just KIV this question, we'll come back to it. Okay, so finally, we just want to end off with the term underfitting. Okay, for sake of completion, we'll talk about underfitting as well. Underfitting is the opposite of overfitting, where your model doesn't even your model that is not able to describe the training data as well as the real the test data. Okay, so it cannot work on the training data, it cannot work on the test data. Okay, this one is very easy to detect. Okay, because when you're training and your accuracy doesn't increase, there's underfitting happening. Yeah, so if the training data if a model doesn't even work well on the training data, no point testing on the test data. Okay, in that case, what can we do? Okay, number one, either get more data. Number two, try a different model. Okay, different models have different strengths, right? So maybe you may want to use this model for you may want to use another model that is better suited for your data. Yeah, so those are two of the things that you can do when you have underfitting. Yeah. Okay, so I'll leave this video in the slides. Okay, you can go and take a look what it means to be underfitting and overfitting. Okay, but you can just take a look at the screen capture here also to see roughly what underfitting, overfitting looks like. Okay, so for example, in a regression question where I have a curve, clearly my data is in a curve, but I purposely want to draw a straight line. Okay, obviously it's not going to model the peaks and the valleys. Okay, the middle one is well fitted because it models the shape of my data. Okay, the last one is overfitting because it tries to force its way through every single point, okay, but then it doesn't show the pattern of my data. Okay, classification, the first one is underfitting. Okay, this one line is doesn't separate my two classes at all. The middle one is nicely fitted. Okay, where yes, there are some misclassified points, but those are outliers, right? We don't want to do you want to go too detailed or too strict to in order to classify everything completely. Okay, this is a nice general pattern, a curve, okay, to cut away my circles from the crosses. Okay, the last one is overfitting. Okay, where I purposely move my line so that I can exclude this x, okay, and this other x. Okay, this is doesn't have a nice shape to it, so therefore this we call this overfitting. And if we give it new data, it may not do very well as well. Yeah. Okay, so overfitting, underfitting is a bit like a Goldilocks problem. Okay, it's either too hot or too cold. Okay, so you need to find that just right fit. Okay, and having your training set as well, training, validation, and test set will help you define that just right fit. Okay, so what are these three sets? We will talk about that when we do our hands-on practical in the next lesson. Okay, so that's all I have for today. Okay, I do hope that you have gotten a better understanding of what supervised learning is about. Okay, what are some of the algorithms that we can use for regression, as well as some of the algorithms for classification. And today we also talk about what hyperparameters are, things that we need to choose on our own in order to help our program learn better. Okay, then we also talk about overfitting and underfitting, and how we can, and next lesson we'll talk about how we can get that just right fit. Okay, so that's a teaser for future lessons as well. Some of you may be thinking, what about neural networks? What about deep learning? Okay, I know deep learning is also an algorithm that we can use for supervised learning, right? So I understand deep learning is actually one of the most exciting, most commonly used algorithms for supervised learning right now, because it is one that almost reliably gives a good answer for almost any kind of data. Okay, so that one I will do a separate lecture on it, all on its own. Yeah. Okay, but for now we'll just stick with these few. Okay, so until next time, I'll see you again. Bye bye.